So far, we have been dealing with the wave solution, the solution of the wave equation for a general time dependence. Now, there is one case of very specific interest, in this, which is the case in which we have a time harmonic excitation. Now, in that case, we are assuming that our generator or our excitation has this sort of time variation, a harmonic representation, a cosine function at a given frequency with a certain amplitude and phase. Now, it is easy to show that for this excitation, any solution of Maxwell equation has this form. It always will be a harmonic, will be also a harmonic expression, a harmonic function, in which with the same frequency, only with a change in amplitude and phase. Now, we can express this function f as the real part of a times a e to the j omega, where now a is a complex number that has a certain magnitude and phase. We will call a phasor. Now, notice that with a time harmonic excitation, now the unknown for any field is just knowing the magnitude and phase of the response, because we already know that the response will be also a harmonic function with the same frequency, and our unknown is just magnitude and phase. And these unknowns are represented by phasors. It is also important to notice that with time harmonic excitation, time derivatives are replaced by just multiplying by j omega. So now we can write Maxwell equations with this for time harmonic excitation in the following way. Notice that the big difference, and you can compare with what I have written in my t-shirt, is that the time derivatives are replaced by j omega, but also it's very important to realize that although we are using the same letters, d, b, rho, e, h, j, but now all these letters are phasors, that is, they are just complex numbers that will tell us the magnitude and phase of the harmonics function that is representing them. Now, in that case, when we use this time harmonic representation, this is the wave equation, and if we go to the one-dimensional case, we can see that we can write it in the following way. We have this space derivative k square, and where k square is omega squared, that's the frequency, mu epsilon. And we are using the letter phi just to represent either the electric field or the magnetic field. Now, the solution for this equation, for that wave equation, is given in this form. A, certain complex number, the phasor, and this exponential function, which that is a wave traveling in the positive sense of the z-axis, and this is a wave traveling in the negative sense of the z-axis. And of course, if we want to know what is the time representation of these solutions, the only thing we have to do is take in the phasor, multiply by a to the j omega t, and take the real part. So this is the time representation of that solution. And this is the standard representation we have. Notice that this is different from what we had before. Now we have the electric field, the red lines, we have the blue lines that represent the magnetic field. They are still orthogonal, but they have this time variation, which is a harmonic function, and there is an important parameter, which is the wavelength, that somehow is telling us the distance, or if you want, the space period, the space period of that wave. Now notice that this is something different of the sort of representation we were using before, and this is the common case we will find when we have this time harmonic excitation. Now, what changes now? Well, it is important to have the notion of the time average of a time harmonic function, and if we have two phasors, A and B, the time average of their period, of their product, is given by this. It's 1/2 the real part of A times B complex conjugate. And in the case that the two phasors are the same, the time average in that case is A times A complex conjugate, and this is 1/2 of the magnitude square of A. Now, these concepts will be important when we have considerations about power and energy using phasors, that is using the time harmonic representation.